Hello everyone, and welcome to today's webinar. We'll be talking about ground bond and ground continuity testing. Before we get started, I would like to introduce the staff here. My name is Prashant Patel. I'm the applications engineer here at Associated Research. I'll be your presenter for the webinar today. I also have Anthony Arroyo. He's going to be the panelist for the presentation today, or webinar today. And then we also have Brittany Socha. She's the organizer for this webinar. A few webinar notes. Those of you that attended this before already know some of the things we do on the webinar. There's a question and answer utility which Anthony is going to be answering live. So if you have any questions about the material that's being presented, please use the question and answer utility provided by WebEx or GoToMeeting that allows you, Anthony to answer the questions for you. If you have any questions or concern about audio or visual that's not showing up properly, do message Brittany Socha using the chat box. And then if you'd like to get a copy of this presentation emailed to you, you could also contact Brittany Socha. Her email address is listed here, is brittany.socha@arisafety.com, or you could just use the chat box to ask her a question. Before we get started, I wanted to go over what we covered in the last webinar. The last webinar really covered the HiPoT test. We looked into detail of how the HiPoT test is performed, what kind of electrical circuits are being tested for the HiPoT test, and what kind of test parameters to be used. We looked at some of the standards that kind of go over HiPoT test parameters and what kind of requirements that come through some of these standards. And we also looked at some of the failure condition that a HiPoT test could detect. So if your insulation was breaking down or if your leakage currents was too high, this may fail your product in the real world. So HiPoT tests kind of covered all these questions that you might have. If you want to review the HiPoT test webinar, it's available on our website under the archive session. Today's webinar will also be archived and will be available on our website in a few days. So for today's webinar, I want to go over the second most important test the standards do ask you to perform on your product. So if you're a device manufacturer, it could be any device like a household device, medical device, it could be an IT equipment or luminaries. All these equipment manufacturers have to concern themselves with grounding their product. Now, we're going to go over how these standards define ground bond and how these standards define ground continuity. And we'll go over which products will require ground bond versus which product will not require ground bond testing, and also cover where these standards come from. So before we get started with the DUT, I would like to cover what is ground and what is the importance of having grounded DUTs or grounded appliances or grounded products, and then cover some of the differences between Class 1 and Class 2 products. Then I'll go over some of the ground bond test parameters, ground bond functionality, and how the ground bond test is performed, and also take a look at what are the most important factors to consider when you're looking at ground bond testing. Same goes for ground continuity. When you're doing a ground continuity test, what is the standard really asking you for when you perform a ground continuity test? Also give you some examples of what is a ground continuity test and what is a ground bond test. And in the end, then we'll do a comparison between ground bond and ground continuity, and maybe have some. We also have some videos that demonstrate how a continuity is performed versus how a ground bond test is performed. So what is the ground? Now, ground has a lot of different definitions, and depending on who you ask, you might get different answers from who you ask. There's some terms that define ground as a reference point for electrical circuits. So when we're talking about any kind of electrical component that's in your PC or in your phones or anything like that, they have a reference circuit or reference diagram that kind of show this is a ground reference. Now this could be an internal reference or an external reference, but this is meant to be as a return path or a low side of your circuit. Now when we're talking about the ground that's provided by the utility company, this ground is usually meant to be a protection mechanism for any kind of fire hazard in your house, any kind of electrical shock hazard in your house or work environment. Usually this is a service ground as defined in National Electric Code, or service ground defined in any kind of OSHA requirement. So if you ever have a utility station providing you power to your building or facility, they usually have what they call service ground. This second image here kind of describes what a service ground looks like. This provides a path for any kind of fault current or any kind of electrical charge that's being built up by either transient or any kind of lightning storm that may hit the area. If the charge was built up in your product or station or system, this provides a proper path for the discharge of this buildup of charge. And I mentioned earlier that it could be also a common return point. So a ground is not only a safety mechanism, it could be also a return point for a circuit. So when we're talking about ground in the household, and we're talking about ground as grounded to the main input of the building. Now, if you take a look at the modern power distribution system, your utility company provides you power. There's always a chance that any lightning storm that comes through that hits the lines, or any kind of high voltage surges that come down the line, could effectively cause fire hazard in the house or cause fire hazard at the utility station. So what they do is effectively ground the system at the entrance of your building. If you look at the image on the left here, under normal circumstances, all the power that is being drawn by your house or equipment in the house, the normal circuit is flowing between line and neutral. And an event of a fault that may occur, so a fault could be line shorting to the panel in your panel box, or something that comes open and shorts to ground. Now in that case, this is actually a fault that has occurred. And in this case, if the fault has occurred, there should be some system that deactivates the voltage coming into the house. And this mechanism is usually the breaker panel that are installed in your house, or it could be also, if it's a big enough short, it could be also a breaker that's tripped at the utility station, which is pretty rare. But an example here is that if you didn't have a properly grounded system in your house, you're potentially having people exposed to electrical shock. So when you have, when you're providing these kind of appliances, you're providing equipment for household use or any kind of system use, if not having a proper ground allows the product to bypass the safety mechanism. Again, so defining a service ground, this is a ground that's meant to protect machineries, transformers, motors, to protect the instrument and the installation around the instrument. It is not meant to protect any of the operators that may come in operators that may use the product, or any end user that is using the actual product. The service grounds are also protecting the house from catching fire in an event that fault current has to go through the wires. The service ground takes care of the charge. Now, an equipment ground is different. So an equipment ground or a product ground that's on your appliance or any products that you manufacture, this equipment ground is there to prevent or provide a layer of protection for the end user, or provide a protection for the operator. Now, the protection we're talking about is the shock hazard, and then any kind of buildup of charge on this product is safely dissipated through the ground circuit of the equipment ground. Before we talk about the types of tests to be performed, we have to clarify what the different classifications are. Now, when we're talking about electrical safety testing, you could have your product classified as either a Class 1 product or a Class 2 electrical product. Now, in this case, if you were to think about a Class 1 product, think about a line cord that has line, neutral, and a ground pin. Now, having three-prong connector like this indicates you have a Class 1 product. Now, Class 1 products has basic insulation that protects the end user from any electrical shock, plus provides an additional layer of protection by having a grounded ground circuit. Now, Usually, if you have any kind of metal enclosed product or any kind of metal accessible part on your product, you're required to have some kind of Class 1 designation on your product. Compare that to Class 2 products. You've probably seen your some kind of product like your iPhone charger that have Class 2 power connections like this. This only has line neutral but does not have any ground pin. The reason for this is that they have dual layer of insulation. They provide 2 layers of insulation compared to a single layer of insulation for Class 1 products. And also, there's no metal accessible part. Everything you could touch on your these Class 2 products is mostly made out of plastic. If there's any screws, the screws are recessed in there that you can't come in contact with it, or it's majority made of plastic. But the protection is still 2 layers of protection. There's a layer of insulation, and there's an extra layer of insulation on top of that. Now, I mentioned earlier there's some products that you don't have to run continuity tests. Obviously, for Class 2 products, since there is no ground circuit, the Class 2 products, which are these right here, there's no need to run continuity or ground bond test since there's no ground circuit. Now, when we're talking about Class 1 products do have a ground circuit. They do have metal accessible part that a person or end user could come in contact with, and this is what we're trying to make sure that the ground circuit is available and able to carry current that in an event of a fault that may occur. Now, where does the definition of ground come? So there's a lot of different areas of definition for a ground, but we have to go with the proper definition of ground. So when we're taking a look at the National Electrical Code that defines a proper ground, and then we're looking at some of the OSHA requirements of what a grounded circuit should be. Some of the definition you could look up is a National Fire Protection Agency 70, the book that kind of calls out for definition of grounding circuit. There's also a definition of grounding versus bonding. This is to protect people and property from electrical hazard. So as most of you are aware of that, the line voltage coming out of the wall is capable of killing people if there was a fault that may occur. In this case, there's definition that kind of cover how this protection should be implemented. Some of the definition might include any exposed non-current carrying metal part of your plug connected equipment may become energized and shall be grounded. So this is defining any metal accessible part on your product may become energized due to lightning storm or maybe some kind of surges on your power line. If that metal becomes energized, you have to be able to safely discharge that charge through some kind of grounding system. Now, some of the additional definition in the National Electrical Code, make sure it needs to be a permanent and continuous ground. The capacity to conduct fault current. So many of you know the breaker panels there in US households are usually rated for 15 amps, but the 15 amp rating is usually meant for, it still allows a certain amount of time before the 15 amp could trip that breaker. The higher the current flow, the faster the breaker would trip. So it needs to have a capacity to carry more than 15 amps of current. It's possible that the breaker or your ground circuit may see more than 15 amps of current. And another definition which is really important when it comes to ground bond testing is that the low impedance or low limit voltage to ground. Well, this defines what the resistance of your ground circuit should be this impedance, it kind of makes that the electrons, when they're in a situation where there's a fault that occurred, always take the lowest resistive path to ground. If you were in contact with this product that was there was in a fault condition, the electrons would see a human body as 1,000 ohms of resistance, or there's a ground circuit that's almost 0.1 ohms of resistance to ground, and they always will take the 0.1 ohms of resistance to ground compared to 1,000 ohms of resistance. So ground bond and ground continuity testing. So when it comes to product safety, when it comes to electrical safety testing of the products, ground bond tests and ground continuity tests are called out for in mostly all the standards. So what's the purpose of this? The purpose of the ground bond and ground continuity is designed to check for ground connection. So you have a ground circuit on your product. So let's take a Class 1 product that has a ground pin. you have a ground circuit in there. You want that ground circuit to be used if there's any kind of shorts in your product or any kind of defects in your product. You want that ground circuit to be a layer of protection. But if you provide the layer of protection and if you don't test that layer of protection, there could be a miswire where the ground is not connected and you're still passing out selling products that are defective in one sense. They also define a proper ground. So we're ensuring a proper ground is in our product before we ship out the product. Now the method we use, it varies depending on what test is being called out. For a simple thing as a ground continuity test, usually the test calls out for a small current test, less than an amp, to be passed through your ground circuit. Now the continuity is, as its name implies, it's just a continuity test. It does not care about how much current your ground circuit will carry. It only cares about if there's a continuous path from one end of your product to the other end, and normally it's the ground pin to the ground stud of your product. So if there's a continuous path there, we're assuming no one made design changes from when it was tested in the prototype phases, that the ground circuit is still there and is still wired up properly. Now, when it comes to ground bond testing, this is more strenuous test, meaning it needs to be able to carry up to 40 amps or 60 amps of current for a specific amount of time listed in the standards. So I've seen standards call out for a 60-second test at 25 amps. I've seen standards call out for 120-second test and about 40 amps of test. So these are all defined in the standards that you're trying to comply to, and majority of the time, most of your ground bond tests are required in your design phase, your prototype phase, and when you're actually coming up with the wiring or the bonding ground circuit when you're designing those things. When it comes to production testing, they're only asking you to verify your ground continuity, make sure the path is continuous. Now, if someone made a change between this where you made a design of a product with this particular wire gauge during your design phase, but then when you go to production, somebody bought a different line code, for instance. And we handle these calls where, as an application engineers, we run into these calls where they use our equipment and they ran all their tests during prototype phases. Everything was passing for ground bond, ACW, HiPod, and all that. And then when they go to production, now they're not passing anymore. So it turned out that in the end, they had bought some cheap line cores, which was not part of the design when they first designed it. So when they were designing the product, they used good line cores. When they went to production, they bought cheap line cores. Now, the customer was checking for ground bond during production, and they were able to catch the fault before they shipped out a lot of products with the wrong line cord. So again, generally the ground bond test is during type testing, which is also called prototype testing phase, and continuity is generally left for production type testing. Let's take a look at what the wiring diagram looks like for a ground bond test. Now on the right side, you see here we have a fan that has a metal accessible part, and having a metal accessible part automatically makes this a class 1 product, having a ground pin. So for a ground bond test and a ground continuity test, we're only worried about the ground circuit of this product. So at this point, the fan would never turn on. We're injecting high current coming out of pins 5 and 4. We're injecting high current onto the ground pin. We're going to let the current pass through the line cord of the product, through the chassis of the fan, which is going to be the metal part, metal accessible part. Now sometimes the fan may be coated with some kind of resistive material. At that point, either you have to look for a screw or look for some scraped off paint to perform a proper ground bond test. Now one thing I like to mention here is that this is our upcoming ground bond tester. It's the high amp series tester, 3200. The point here is that this makes a 4-wire connection, and I'll go into details when I show you the circuit diagram. But the point of when we're measuring such a low resistive circuit, we're measuring 0.1 ohms, and we're outputting 40 or 50 or 60 amps of current. To be able to measure down to 0.1 ohm accurately, you could use a method called the Kelvin method. With the Kelvin method, known as a 4-wire measurement, you have 4 different wires. two on each side. So you're applying with two wires and you're returning with two wires. One of the wire is thick enough to handle the current. The second wire acts as a voltage meter that allows you to bypass any of the resistance that may be added on due to the system. So what do we define as a system? Any kind of internal resistance to the tester, any kind of resistance that comes from the test leads. So you want to be able to offset this and not count it towards your product, because your product doesn't really start till the ground pin of your adapter and ends at the metal chassis of your product. So if you had maybe 5 feet of cable or 10 feet of cable before you got to the your product, every feet of cable would add some kind of resistance. And since we're measuring such a low resistance, it's imperative to kind of offset any resistance that the test leads might provide. Now we have a functionality other than the 4-wire measurement automatically takes out the resistance of the wire, but additionally you could perform a test where you're shorting these two leads together to provide a known resistor for these wires, and you could use that as an offset feature. But again, this is some features that you could use to properly test your ground circuit. And this is what a connection looks like to a product. Next, we're going to take a look at what a circuit diagram looks like. For ground bond testing, again, on the left side, we have an instrument that outputs high current. The current is going to be injected through some kind of receptacle box on our, so on the left side is our instrument outputting the high current, the ground bond tester. And the ground bond tester is injecting high current onto the ground pin of the product. Now that ground pin should be connected internally to the ground of your DUT, device under test. Now this DUT is usually has some kind of internal resistance, ground resistance, and if it's metal, then it's going to have some metal chassis point there where you can connect your return point to. Now once you connect your return point to our tester, we have two ends of the leads connected to the product for our current to pass through it and to see if there's enough capacity for this ground circuit to handle that much amps, plus not go above the requirements that are listed in the standard of 0.1 ohms or 0.2 ohms, depending on what standard you're following. So let's take a look at what a pass would indicate. So when I press test on my instrument, it's going to start injecting high current onto the ground pin. All that current goes to the ground circuit of the product. The return is measured on the chassis of the product, and the green would indicate that it was able to handle 25 amps of current without opening up or causing any damage. Plus the resistance of this ground circuit did not go above 0.1 ohms or 0.2 ohms. Again, we want to make sure the ground circuit, it has a low resistance value or low impedance to ground, because this is what protects end users or customers that may come and touch this product in the event of a fault that may occur. Now, failure could mean two things. Either the ground wire is not connected to the chassis. In that event, you don't have a properly grounded product. So either the product is not connected or the resistance of this product is more than 0.2 ohms. So again, we want it to have a really low impedance to ground. If you have anything higher than 0.2 ohms or 0.1 ohms according to a standard, this will indicate too much resistance to ground, and this will be a failure mechanism. Our instrument will indicate a failure, usually report a failure saying greater than 20 milliohms, or sorry, not 20 milliohms, greater than 200 milliohms. Now, if the wire was not there at all, let's say somebody in production forgot to screw on the ground wire to the chassis. Now, here the ground test would indicate an open circuit. An open circuit is nothing more than infinite resistance, so the instrument is still going to detect more than 0.2 ohms or more than 200 milliohms. Some of the standards that we look at when we get inquiries in, one of the major standards we deal with is the medical standard 60601-1 3rd edition, which is a current edition. Now, if we concentrate on this standard, the clause 8.6.4 indicates what kind of requirement you should have for your ground bond test. So if I just read it directly from the requirement, it requires you to apply 25 amps of current or 1.5 times the highest rated current pass to the protective earthing circuit. Okay, so this is telling you to apply 25 amps to your product ground circuit, ground pin to the chassis, or apply 1.5 times the highest current. So if your product drew 10 amps of current, that would be 15 amps, but 25 is higher. So you would want to use the higher of the number. So 25 amps would be the current level for your ground bond test. Now the frequency is also defined. It could be 60 or 50 or 60 hertz, and most of the ground bond testers out there comply with this no load voltage of less than 6 volts. Our instruments go from 2 volts all the way up to 12 volts, but this range is something that you could adjust on our products. Now let's look at, that was a requirement for the testing parameters. What are the pass parameters or requirement to pass a product's ground circuit? So a medical standard, which is really stringent on most of the electrical safety parts of the standard, it requires that the impedance protective earth circuit on the device and the test should be less than 100 milliohms. Again, we're talking about 0.1 ohms of resistance for your ground circuit. For DUT that has non-detachable supply cord, the impedance could be less than 0.2 milliohms, or sorry, less than 0.2 ohms or 200 milliohms. In this case, you could see there's difference within particular standards too that allow you for different kind of resistance numbers depending if you have a detachable cord or an attached cord. Now, before we go on, I do want to put up a question here. The question for today, so I have Brittany put up a poll question for today, and I wanted to get an idea of how the standards are being implemented. Is there somebody at the facility or your company that allows you to come up with the test numbers or test requirements, pass or fail criteria? Is it something that you, the NRTLs help you, like the National Testing Laboratory, UL, TUV, Intertech? Are those the companies that provide you the pass-fail criteria, or is it something that you learn on your own and contact the manufacturers directly, or some that may not have the idea of where to get these numbers and need more training? So I'll give a few seconds for you to fill out the poll.
All right, Pashan, we've got our results. How confident are you in the translation and implementation of your standard? 30% said very confident, 43% said confident, 27% said not confident, and 0% said positive, I'm doing something wrong.
Okay. Well, thanks everyone for submitting the poll. So I do see a lot of people that still have questions about the particular standards. There's a standards guide that we provide, and I could have Brittany provide you a copy of this. This standard guide provides you some of the information we just saw on the previous slide. This comes directly out of our standards guide to show you some of the parameters called out for in a particular standard when it comes to ground bond testing. Now, not only this guide contains the ground bond parameters, but it also contains the HIPAA test requirements or any kind of IR test requirement you may have. Going forward, just to look at a few other standards, and again, the standards guide will provide you some of the main definitions of it. If you really wanted additional help with this or additional questions that you may have, you could obviously reach out to us. If you're using our product, then we'll be more than happy to help you come up with some of the pass-fail criteria or go over some of the test parameters that you may be currently using. Let's take a look at luminaries. It's a big market with the LEDs right now, where UL 1598 that concerns with luminary products. Now here the test current requirement goes up. So the 30 amp, now the current required here is 30 amps of current. Now during a production type testing, during a prototype testing in your design phase, this test time is listed here for 60 seconds to 120 seconds. Again, 1 to 2 minutes of testing to make sure your ground bond circuit could handle 30 amps of current without going over the resistance value. So you could see here, this is a lot of current being passed through the ground circuit, and when the luminaries are tested or prototype phase, they're being tested to make sure they handle 30 amps of current for an extended period of time. The pass criteria here is also less than 1.1 ohm or 100 milliohms. This is a requirement that comes straight out the UL 1598. Another standard here, 603351. This also requires you to have 25 amps, and another similar requirements of having less than 100 milliohms of resistance on your ground circuit. There's some standards do also call up for voltage drop, and our newer instruments do have this new option called voltage drop. So if your standard calls out for, instead of resistance value, it says, okay, you cannot drop more than 2 volts across your ground circuit, we have the solution for that. Our newer instruments does display voltage drop. You could have a voltage high limit set, a voltage low limit set that allows you to not do the conversion outside of the instrument. The instrument does the calculation for you. Basically, we're using the same formula, Ohm's law, V equals IR. We are already measuring the voltage, but the resistance is displayed as a calculation. So we talked about ground bond testing. This is testing, ground bond was testing the integrity of it. You're making sure the ground circuit can handle that amount of current for that specific amount of time. Now, you will see a lot of the standards, and most of the people that work in production, they're not concerned with the ground bond testing. They just want to pass the ground continuity. Why? Because majority of the standards, if you look through it, even the medical standards, usually call out for just a continuity test. Well, what is a continuity test? A continuity test defined in terms of current is just a low DC current to check for a continuous path. And then it doesn't even require any kind of numbers for your ground continuity test. Some of the standards just say a simple buzzer or a light that goes off is a clear indication of continuity. So there might be a continuous path, but you don't know if the guys in the production are screwing in all the strands of the ground wire, or maybe one strand of the ground wire is connected. In this case, you will get a good continuity reading, but if this product were to go out to in the real world, if any fault current were to happen, it would not be able to handle fault current, and the circuit will break open on the first time it tries to handle fault current, and the next time somebody comes in contact with it, this creates a potentially shock hazard condition. The methods obviously I described earlier, light buzzer combo. So light or buzzer that goes off indicates a continuity is sufficient enough for a continuity test. Not all readings require some kind of ohmic resistance compared to how a ground bond test was. It was requiring ground resistance to be displayed. Now, we do recommend that if you have the time, if you have the time in your production line to perform the ground bond test. If you're performing the ground bond test, it automatically covers you for the ground continuity test because you're testing the same circuit at much higher amperage than what's required. So this is like going above and beyond what's required in the standard. So if the standard requires you to just check for continuity, but I'm a medical equipment manufacturer and I want to make sure that everything that leaves my facility not just tested to the minimum value, is tested to more than the minimum value. So in this case, I'm going to do a ground bond test because I'm selling somebody a $25,000 equipment. I'm selling somebody a $100,000 equipment. I want to make sure the ground circuit is there, plus is working properly after the production is done. So what do I mean by standards calling out for continuity? Let's take a look at an example of 61010-1. A routine test. Again, a routine test is your production line test. This is done on 100% of the product that you ship out to your building. It has to be performed on everything that is being manufactured and shipped. This is similar to a HIPAA test, right? You want to be able to perform the dielectric stand test on your product to make sure there's no bad insulation. So that was checking the insulation. Now here we're checking to see if there's continuous path to ground. So let's take a look at what the test actually calls out for. A continuity test to be ran on protective earth circuit, and this basically calls out for no current value was specified, no other parameters were specified, and this is actually talking about a continuity, just to make sure there's a continuous path. Another standard here, during routine tests, it calls out for 10 amps of current. Again, this may look like a continuity test, but it's not. It's more of a ground bond test. You have a 10 amps of current flowing through the ground circuit of your product. When we define ground continuity, we're defining low current test. Now, this test doesn't clarify and say, oh, this is a ground bond test, but you could see by the current that's being applied. It may not be the full current that it could be seen when this unit is connected, but it at least is testing for more current than what the continuity test is doing. Again, the impedance requirements are listed. For appliances, they're for corded equipment, it allows you up to 200 milliohms of resistance, or all the other appliances are not cord connected of 100 milliohms of resistance. Again, this is directly out of our standards guide, and a copy could be provided by Brittany in the chat box. So let's compare ground bond versus ground continuity. So during a ground continuity test, you're just verifying an existence of a ground circuit. Ideally, there's resistance is given in ohmic number. This is a really quick test to be performed, and is generally required to be performed on 100% of your production line products. We have our products, our HiPoT tester, that come with built-in continuity tester. This allows you to easily perform the most commonly performed electrical safety test, the AC HiPoT test, and the second most commonly performed electrical safety test is the continuity test. So if our HiPoT testers give you the capability of performing ground bond and ground continuity and HiPoT test, this meets most of the standards that call out for routine continuity tests. Now, when we go over to ground bond testing, now we're upping the amperage here. So we're stressing the ground circuit, or checking the integrity of the ground circuit to make sure it could handle the 15, 20, 25 amps, up to 60 amps of current. So ground bond circuit needs to be capable of handling up to 60 amps of current. Now, again, the readings are also given in milliohms, and as we saw earlier in some of the standards requirement, 100 milliohms, 200 milliohms generally gives you a good idea of what the resistance of your ground circuit should be. This provides a valuable information about the safety circuit of your product. So if I'm able to apply 25 amps of current to your ground circuit, and my resistance is 100 milliohms, this tells me that the product has good ground. And if in the event the fault were to happen, this ground circuit will carry the current and will carry it successfully. So I'd like to give an example here, a graphical example of what we mean. So if you had a stranded wire, so in the exact example, we have a 64-strand wire. Now below the installation, be it the manufacturer defect or some kind of crimping that may happen or scraping that may happen, some of the strands came off. So the insulation is on top of your line cord that you purchased, but inside this insulation, the ground wire, instead of having all 64 strands connected, may just have 1 or 2 strands connected. Now, having run a ground continuity on this wire, you could pass the continuity all day long. It's a low current test. It's not going to damage the wire. It's going to be able to carry the low current from one side of the wire to the other side. It will pass your continuity. So in your production, if you had this wire in your product, you will pass continuity. Now let's think about ground bond. Now if I try to run ground bond test on this one single strand of wire, as soon as I start applying anything higher than 2 or 3 or 4 amps of current, this one strand of wire is not capable of carrying that much current. It's going to open up and indicate a ground bond failure, as there's too much resistance between one side of your ground to the other side of the ground. Now, this ground bond failure could be bad, in fact, where this happens during when the product is being used by an end user. This failure could lead to some potential shock hazard situation where somebody could get shocked. So for our poll question 2, we just want to verify that everything that we covered so far kind of makes sense to everyone. And I'll go ahead and have Brittany put up the second poll question. It's asking about which one is the most strenuous test for of the tests that are listed.
All right, Bashan, we said which test measures the integrity of the ground circuit? 70% said ground bond, 9% said ground continuity, and 21% said both.
All right, thanks very much for everybody for participating. So 70% of the people do get that the ground bond is more strenuous. It's checking the integrity. Now, continuity, again, is not checking the integrity of your ground circuit. So if you're doing a simple continuity test, you have no idea how much current your ground circuit is going to be carrying. So it's really important to understand the difference between a ground continuity, which is a simple test, one strand of wire could pass that test, while a ground bond test, you require all those wires to be there and be able to carry that current and not go over the resistance value. This brings us to our video demo section. So I would like to demonstrate what I mean by ground continuity and ground bond circuit. So first I'm going to show you a ground continuity test being performed on a this is a soldering iron. So let's take a look at that really quick. So here we have our high-amp series tester. One of the parameters there, now the bottom tester is a high-pot tester, which has the ACW high-pot test built in with the continuity. So I'm going to demonstrate how AC high-pot test could be ran alongside with a continuity test. So we have a parameter called continuity. So I'm going to turn the continuity parameter on. The next few parameters allow you to set the high and low limit of this continuity. So again, we're talking about the continuity tests that are called up by most standards during production line testing. Now, you're going to see I set the high limit, low limit, and then I have a little bit of offset to make sure my wire's resistance is not counted. And we're going to see what happens when I connect the product under test. So my product under test is a soldering iron. I'm going to make a connection to the ground pin of this product. When I made a ground connection of the ground pin, you have the light indicating a continuous path. So this is all a continuity test requires. It requires you to make sure that there's a path from any metal accessible part, which is the soldering iron blade tip area, to the ground pin of the product, So this indicates a continuous path, and this is all that's required for a continuity test. Now, if you were to perform a ground bond test, this changes the things, this changes some things about what parameters to put in. So now, when we look at the ground bond requirements in your standards, it'll call out for a particular current amount. So in this case, I'm going to punch in 25 amps of current. Our limits for this tester is available from 1 amps all the way to 40 amps of current. So I'm going to type in 25 amps of current. Again, some standards require you to set the open circuit voltage to be less than 12 volts. Well, if they don't specify any other voltage, we have the range from 3 volts all the way to 8 volts of open circuit voltage. This is my next parameter. Here's my high limit. I've set it to 150 milliohms. Again, the standard calls out for anywhere from 100 milliohms for some of the products to 200 milliohms for other products. So my high limit is set. Anything higher than this limit, any resistance higher than this limit, our instrument is going to indicate a failure for the ground bond test. Again, if you have some standards that call out for, instead of resistance, now they're calling out for the voltage drop. Here's where you could set the voltage drop of the product. So similar to our high and low impedance, which was in milliohms, now we're talking about resistance value, the voltage value that could be dropped. So the standard will specifically call out for a high limit on the voltage drop across your DOT. Low limit is zeroed out for this. And then offset, since we have a 4-wire connection, if you take a look at our product, it has a sense plus connection and a sense minus connection with current and return jacks that make this a 4-wire measurement. It's more accurate compared to a 2-wire measurement, as the instrument has capability of measuring voltage all the way down to the DOT. So when I go through this, I'm going to go ahead and perform a test on this, and I'm going to pause it in the middle. So you see right here, we're applying 25 amps of current. The resistance read back on this ground circuit is 71 milliohms. Now, you can look at the black wire here. It's connected to the chassis of this soldering iron. The red wire, which is injecting the current, is connected to the ground pin of the product. So the current is going in the red ground pin, coming out of the chassis of the product, and the ground circuit is able to handle 25 amps of current, and the resistance is 71 milliohms, which is better than the 100 milliohms that some standards specify. So this is how you would pass a ground bond test if you were required to perform ground bond test on this soldering iron at 25 amps. As long as the resistance stays below a particular ohmic resistance, you get a ground bond pass. Now, one thing to note here is that we start including with our new tester the voltage drop. So if your standards does not care for the milliohms reading and they actually call out for voltage drop, you could actually drag this meter down here, and now you have a measurement that's in voltage. So if the standards call out for do not drop more than 2 volts across your DOT, that indicates I'm still passing it because I'm not dropping more than 2 volts across it. I'm only dropping 1.78. Again, Ohm's law is in play here. So if in the previously most of the equipment or instruments did not display voltage drop, the standards that they require this, it will have to be calculated outside of the instrument. All right, so that's the demo of the HIPOT test. Ground bond test being performed on the soldering iron. Now, I want to take this over and kind of demonstrate what happens to our one strand of wire. So if I were to show you an example of a paper clip, so again, same test is being ran. We're going to run a continuity test first. Two sides of the continuity test. One side is injecting low current. Other side is taking the return current back to the instrument. And to pass this test, all you have to have is a continuous path. Paperclip is kind of like a strand of wire. It passes as a continuity test. So let's take a look at our HIPOT tester, see what it indicates. Again, a green light, a light or buzzer combo indicates a continuity test. If I were to disconnect that wire from one end, this green light would go away, indicating there's no continuity. That's a failure. As soon as you press test on our tester, it will say continuity max or continuity failure, depending on what instrument you have. So again, this is showing you what a paperclip demo looks like. And now we're going to switch over to the actual ground bond test. Now, if we were to perform a ground bond test on the same paperclip, you could see applying 25 amps of current on one strand of wire, that's what it caused. So this, I'm going to rerun that again really quick. This is applying 25 amps of current on that same paperclip that passed ground continuity. If this was your product that had one strand of wire and you check for ground continuity, it goes into somebody's household and some fault had to occur, this could literally cause fire hazard. And that's why these standards come into play, the National Electrical Code, National Fire Protection Agency, OSHA requirements. They want this ground wire to be proper and to be able to handle current so this doesn't happen and catch fire for the stuff inside the walls to catch fire, or even the product to catch on fire. Again, I like to rerun this really quick to show you the effects of applying 25 amps of current to a single paperclip. Now the resistance initially might have been something, but now is opened up. So this is an open circuit, and this is what a ground bond failure would indicate in your product. So just to summarize here, Those demos showed you a difference between a continuity test and a ground bond test. Again, we took a look at what ground is, how ground is defined, where to look for a proper grounding requirement. So if your house is newly built home, it might be up to the code, meaning it's up to the National Electrical Code, National NFPA code, whereas grounding is grounded properly all the way back to the source, or there's a grounding stake outside of your house that's doing an equipment ground. We talked about ground bond tests, how some of the standards call out for ground bond during type testing, and then we also define ground continuity and where the ground continuity comes into play for your product safety. And in the end, we compare both the ground bond and ground continuity. Now, I'd like to open up for any questions that you may have for the presentation, or if you have any other questions about either ground bond or any kind of electrical safety testing, either you could type out the question and I will have Tony read it out to me. While he's doing that, I'd like to point out that our next webinar is about Audit Survival Guide. This will be Wednesday, July 12th, same time, 10 a.m. Central Time, and we'll be going over what kind of things to be on the lookout for when you're going through some audits or preparing for audits, you know. Also, if you do want to contact us, you could use our website, arisafety.com. This includes all our product offerings on our website. Also, you could email Brittany Socha. Her email address is brittany.socha@arisafety.com. So let me know if there's any questions.
Hey, Bashan.
Yes.
Not too many questions. I think you've done a good job explaining the information. One question is, what type of current would the product see on a continuity test?
Okay. That's a good question, actually. And I failed to mention, I did say low current. I didn't mention the param numbers. Now, it varies between manufacturers of the instruments. For us, we have our current listed at 1 amp as a maximum, but it ranges. So it goes to 0.1 amp or 0.01 amp, depending on how much resistance is on your ground circuit. So if I were to define the current, I would say less than an amp is what's being outputted on the ground continuity. Again, that paperclip may be able to handle 1 amp. It doesn't start breaking down or opening up because it's able to handle 1 amp of current going through it. When you stress it, when you check the integrity, okay, now I'm going to see if 25 amps are being carried. The paperclip opens up, burns up, causes fire hazard. I hope that answered the question. Anything else, Tony?
Nope, I think besides that, maybe just to know that all our instruments do come with rear ports. So in that video we were connected to the rear, which is why you didn't see the connections on the front. And then people are asking what is our limit with ground bond testing. So we do have instruments that can go up to 60 amps. And beyond that, I think we're good.
Okay. All right, so thanks everyone for attending the webinar today. Hopefully this has been helpful. If you do want to reach out to us, just email Brittany and we could answer any other questions you may have outside of the material that's been covered here. And see you next time.